Good morning. In this case study, we are discussing about the heat transfer problem. It's kind of one-dimensional heat transfers. Okay. Let's see on the some basic concept for this topic. Our students Karthi, we explained the what is the basic fundamental equations of therein and also general governing equation of heat transfer problem. We are to discuss in below. Okay. So first of all, the heat transfer will be conduction of mode is called as there are three methods, that is conduction, convection and radiation. So in our problem we are discussing only the conduction and convection by using of the finite element method. Okay, so before that using the convection problem, so we need the basic fundamental equations. So what is the fundamental equations of that is called as the stiffness matrix, shape function and temperature, nodal temperature. Okay, these are the basic fundamental equation whenever you have to solve the convection based problem or convection based problem. So our students Karthi, we explain the how to derive the stiffness matrix for one-dimensional heat conduction and the convection problem, and also derive the shape function of the given one-dimensional problem. So let's topic given to the Karthik students. Thank you.
We are going to see about derivation of temperature function and shape function of 1D heat conduction element. So for this derivation, we have to consider a bar element with node 1 and 2, which has a temperature of T1 and T2 at their respective nodes. So T1 and T2 are considered as degree of freedom of the bar. Since the element have got 2 degrees of freedom, it will have 2 generalized equations. T is equal to A0 plus A1x is first equation, where the A0 and A is global generalized coordinate. So the T is equal to, we have a certain matrix which is given as 1x into A0 A1. After applying boundary condition, at node 1 it becomes T is equal to T1, x is equal to 0, and at node 2 it becomes T is equal to T2 and x is equal to L. After applying this boundary condition, T1 is equal to x0 is the third equation and T2 is equal to A0 plus A1 L is fourth equation. If we arrange third and fourth equation in a matrix form, it will be like T1 T2 is equal to matrix of 1 0 1 L into A0 A1. Here the T1 and T2 are degrees of freedom. So 1 comma 1 is a connectivity matrix where A0 and A1 is equal to matrix of 1 0 1 L inverse into T1 T2. The A inverse can be written as 1 by modulus of A into adjacent A, where then A0 and A1 becomes 1 by modulus of A into L 0 minus 1 1 into T1 T2. If we substitute equation 5 in 1, we get T is equal to x into 1 by L matrix of L 0 minus 1 1 into T1 T2. Then it becomes T is equal to 1 by L 1 minus x 0 plus x into T1 T2. The final equation will be T is equal to 1 minus x by L into T1 by T2. The temperature function and shape function becomes shape function N1 N2 will be L minus x by L and x by L, and temperature function T will be T is equal to N1 T1 plus N2 T2. That's all. Thank you.
Thank you.
So the next derivation will be of stiffness matrix for one-dimensional heat conduction element. Here we know that stiffness matrix is equal to Kc is equal to integral of B transpose into D into B dV, which is the first equation of stiffness matrix for one-dimensional heat conduction element. In this one-dimensional bar element, temperature function is represented as T is equal to N1 T1 plus N2 T2, where N1 is equal to L minus x by L and N2 is equal to x by L, which we derived in the previous derivation. And we also know that strain displacement matrix is considered as B, which is equal to dN1 by dx and dN2 by dx. Here the dN1 and dx is calculated with using d by dx of L minus x by L, which is equal to d by dx of L by L minus d by dx of x by L. After the derivation is integrated, it will become 0 minus L by L, which becomes minus 1 minus becomes minus 1 by L. Then dn2 by dx is calculated by d by dx of x by L, which becomes 1 by L. After applying this equations in matrix form, then B becomes minus 1 by L, 1 by L. If we transport the B into B transpose, then it will become minus 1 by L, 1 by L. In one-dimensional bar, the D is calculated using K, which is thermal conductivity of that particular element, where Kc is equal to integral of V, matrix of minus 1 by V, 1 by V into minus 1 by L, 1 by L into K dV. Here, after the integral is applied with the condition of 0 to L, from the limit of 0 to L, where dV becomes area into dx. After applying these conditions, the equation will become integral of 0 to L minus 1 by L, 1 by L into minus 1 by L, 1 by L into K A dx. After giving the values to the x, L and x, the matrix will become 1 by L square minus 1 by L square minus 1 by L square minus 1 by L square into K A into dx. The final form will be K A by L square 1 minus 1 1 into x of 0 to L. After giving the value for x, the value becomes Ka by L square into 1 minus 1 1 into L. The final form of Kc will become Ka by L into 1 minus 1 1. Thank you.